Okay. So I was trying to tell you that even from, between, well, okay, the neutrino stuff was really the 80s, but 30 to 40 years ago, we established that this quark-parton idea was looking pretty good. But there was one problem with it. Now, I told you that this Gross-Llewellyn-Smith sum rule, right, came out around 3. There's another sum rule with the neutrinos. If you just integrate up the F2 structure function, that's the integral of the momentum distribution of everything. So you would expect that the integral 0 to 1 should be 1, right? That's all the momentum. You've integrated up over momentum. Answer 1. Answer wasn't 1. It was 0.5, right? So physicists love doing things like this. They called it an energy crisis at the time, But, okay, with hindsight, it's very obvious where this momentum is going to have gone. It's gone into the gluons, right? And indeed, it's obvious what's wrong with the quark-parton model because we just summed up all those virtual boson parton scatters as if they're incoherent, which suggests that the partons are kind of sitting there, but they don't interact with each other. They're just each free on its own, and the probe interacts with it, but nothing to do with its next door neighbors, right? This cannot be true, obviously, right? And partons are bound in hadrons. How is this happening? It's happening from the interaction of the quarks with the gluons. And the interaction strength of that is called alpha sub s in analogy to the alpha for the fine structure constant. But unfortunately, alpha sub s at normal kind of energies, everyday energies, is large. It's 1. You can't make perturbative calculations with a coupling constant that's that large, right? And this is why, actually, when I was kind of your age, we understood almost nothing about strong hadronic physics because we couldn't calculate it. It was a mess because we were doing experiments at low energy. We were getting results that depended upon non-perturbative calculations. We couldn't do them. We didn't understand any of it. It was as this all emerged, we finally began to realize that if we could only go to high enough energies, then it's a misnomer. You call the fine structure constant a fine structure constant. Even that's a misnomer. It's not actually a constant. But when it comes to the strong interaction, alpha sub s is very far from being a constant. It changes very rapidly with scale, and as the scale goes up, the coupling goes down, and the quarks do indeed become asymptotically free, right? So if you're at high enough energy, they'd be completely free. But even working up at 100 GeV or so, it's gone down to about 0.1 or so. That's not too bad. You can do perturbative calculations with it, and we can finally understand the field. So what are these gluons? They are the force carrier of QCD. In analogy in QED to the photons, the gluons are in QCD, but there's a lot of difference between these theories. The gluons carry the quantum number color. So what is the evidence really for gluons and for color? Now, I don't know if you would have been subjected yet to this kind of argument that we were given when doing old-style hadron physics. We discovered particles in which there were 3 particles that are the same. My example here is strange, strange, strange in the omega minus, but it could be u in the delta double plus or something like that. The same particle, identical particles, the same spin, because they all need to have spin 1/2 together to make a total spin 3/2, right? No orbital angular momentum. In other words, they violate seemingly Fermi statistics because it would overall be symmetric, and you need it to be antisymmetric. And the answer we were given was, well, we'll put the antisymmetry into the color wave function. Well, when I was an undergraduate, I wondered a lot about that. I thought, so they've invented an entire new concept, the color, just to save the Fermi statistics. But actually, there's a damn good reason why you want to save Fermi statistics, right? I mean, it really is a good idea to have invented color instead. Now, since that time, there have been many more evidences for this. You can do E plus E minus scattering. Right? E plus E minus can scatter to mu plus mu minus, you can measure that. More of the time it scatters to hadrons, you can measure that. When E plus E minus scatters to hadrons, it's actually doing it by scattering to a QQ bar pair, which then become the hadrons. If that's the case, then the cross-section for it's going to be extremely similar to mu plus mu minus, because QQ bars are just fermion-antifermion as well. And so the ratio of this cross-section is just a simple sum over the quark charges squared. Right? That's the only difference in the diagrams. When they first calculated it, they really did think they were looking for a ratio sum over quark charge squared. That would have been 2/3 for the known quarks at the time, the U, the D, and the strange. But the measurement didn't come out at 2/3, it came out at 2. Why? Because you hadn't accounted for the fact that these Q and Q bars can each come in 3 colors. Now, the very fact that this ratio was measured as flat at all was a triumph for the quark-Parton model again, because if this process was not going via QQ bar but some other way, there's absolutely no reason why that ratio would need to be flat at all. It was flat, so that was great, but it was flat at the wrong value, which initially people thought wasn't great, but a little bit more thought and you suddenly realized, yes, this corresponds exactly to the idea of an extra degree of freedom. And this argument about the Fermi statistics, actually, your new degree of freedom didn't have to have just 3 ways for that. It could have had 5 or any number to save the Fermi statistics. The fact that this is measured as 3 times what we first thought is why we believe in 3 colors, right? That's part of the experimental evidence. And there's lots more of it these days. If you look at the ratios in which the W's decay to leptons and neutrino or to UD bar or other flavors like CS bar, the ratio of that can be predicted from color as well. Right? The ratios for the leptonic modes are about 11% each, but for the hadronic modes are more like 33. A factor of 3 more because of more color. That's the only reason why they would be more. This is measured. You can do similar things with the Z. I won't dwell on that though, because it's a little bit more complicated. The Z does not couple to U's and charm the same as it couples to D's and strange, right? It distinguishes the up and the down sectors. Nevertheless, the ballparks of the percentages are pretty good for what you would get from just a simple quark-Parton model. But the best reason for believing in gluons is because you can see them. Well, not quite, but you can see their effects, right? So just as an electron radiates a photon, a quark radiates a gluon. And the strength of this is the square root fine structure constant, this of the square root of alpha sub s. The number of these photons is 1, the number of gluons is 8. Why not 9? We'll come to that. And if you observe the process E plus E minus to QQ bar over mu plus mu minus, you can also observe that they have the same differential cross sections, the same scattering angles. So I told you already about this one being a simple ratio. You can also do E plus E minus to mu plus mu minus and a photon, that can be measured, and you can do E plus E minus to QQ bar and a gluon. These are going to be similar to each other. But it's no good my just saying that. Let's show you. Right. These are actually pictures from the LEP collider. This was an E plus E minus collider at CERN, right, running from 89 to 2000, and was actually, I mean, the W's and Z's had already been discovered, but what the purpose of this was to run the E plus E minus exactly at the center of mass energy of the Z and create thousands of them and really study what happens in Z decays. And it did other things as well. But these plots are showing you the analogy. Here we're looking down the beamline, right? So the E plus E minus coming in interacts and becomes an E plus and E minus going out in that picture, right? Below it, E plus E minus and a photon radiated coming out, right? Now, you can also see very similar things happening. Here, E plus E minus went in down the beamline and out came Q and Q bar. you're not seeing exactly the quark and the antiquark. What you're seeing is the jet of charged particles that they create as they come out of the proton, right? But it's very clear when you look at this how similar that is. And so when we look at the analogy to E plus E minus photon, we see Q bar gluon, right? Again, 3 jet events. This was the first signal that there was for there being gluons. And in fact, there is more radiation involved with a gluon than there is with a Q and a Q bar. Now, admittedly, I can't really tell when I look at this Q and Q bar. Of course, I don't really know which one was the Q and which was the Q bar, right? But actually, I do know which was the gluon because gluons radiate more. Gluon jets are, on average, kind of fatter. There's more stuff coming out with them, so you can usually tell which is the Q bar. So this is really why we believe there are gluons, because we basically think we've seen them. Okay, now, all right. A little bit heavy, but just to make sure we've got all this correct, right? The analogy between QED and QCD, right? QED is a locally gauge invariant field theory. That means that the wave functions do not depend upon where you are, essentially, and that's encoded in this phase, e to the q theta, where q is the charge, like electron charge, and theta is a space-time dependent phase. The Lagrangian for QED has this piece, which tells us about the interactions of the fermion psi bar with the vector field, right? And that's the covariant derivative d sub mu involving the vector potential of the field. And then this is the bit appertaining to the field itself, encoded in f mu nu in terms of these covariant derivatives of the vector potential, right? So hopefully that U1 field theory is reasonably familiar to people, right? And then going on from that for QCD, the phase transition it's a bit more complicated. It's not just q theta, it's g t dot theta, where g is the strong charge, like E for the for QED, and t dot theta is a product of color group generators with a vector of space-time phase functions. The group we're talking about here is SU3. It was U1 in this case, it's SU3 for QCD, right? The group generators, these, the T, are given by these commutation relations in terms of the SU3 structure constants. And the T's themselves can be written in terms of the Gell-Mann matrices, lambda over 2, and there are the Gell-Mann matrices. One thing you can notice about them is that subparts of them look very much like the Pauli matrices, right? So the quark part of your QCD Lagrangian looks like the quark part of the QED one, but the derivative D has become more complicated now, involving the T generators and the color vector potential, right? So there are many more indices here to indicate the fact that there are the 3 colors. And that bit describes for us the quark-quark gluon interaction, right? Where the quarks now have the color indices 1, 2, 3 for red, green, blue, as well as their flavor indices. And the gluon fields have 8 flavor indices. So let's look at that. Right? The color exchange, say in a simple case, looks like this, with a red quark coming in, and let's have anti-green on an outgoing anti-quark there, so that the color of that gluon is red anti-green, right? Red green bar. And you can make up for yourself what the other possibilities would be, the red blue bar, green red bar, etc., right? Those are the obvious things you do. And then there's the slightly non-obvious ones where what you're combining is things of the same color, red, red bar, green, green bar. Well, one minus the other by root 2. Red, red bar plus green, green bar minus blue, blue bar over root 6. And red, red bar plus blue, blue bar plus green, green bar by root 3. Now, why that particular structure, which just looks arbitrary? That's because it's what SU3 tells you the structure is going to be. And if all this is looking a bit strange, right, the mathematics of this, right, of SU3 is that 3 colours in the quark and 3 anti-colours in the anti-quark, if you like. 3 times 3 makes not 9, but 8 plus 1. That's the structure of the way it breaks down into octet and singlet. What is the singlet? It's this one, because this has absolutely equal amounts. Red, red bar, blue, blue bar, green, green bar. In other words, it's not overall coloured itself. The colour has all cancelled out in that one. There is no colour, and that's why there are only 8 coloured gluons, because the 9th one doesn't have a colour and hence doesn't couple to anything. And if this all looks a bit weird, 3 times 3 is 8 plus 1, you do know about it really, because you must all have studied atomic physics when you had to add together the spins of 2 electrons and you found you got a triplet and a singlet, and that was nothing other than SU2. 2 times 2 is 3 plus 1. Right? This is just the generalization of the group to the next dimension. So if I summarize what we can have in terms of the colored gluons, they're here. Now, so far I've only dealt with the quarks, quark-antiquark interacting with gluon vertex. There's also the second part of the Lagrangian, which looks as it did in QED, except that the F functions now don't just have this piece, they have an extra piece in terms of the SU3 structure constants. And what that means physically is this extra AA term means that gluons also interact with gluons, right? In QED, the photon only interacts with the charge. It doesn't interact with itself. There's no photon-photon interaction. In QCD, there is. So you get not only these vertices, but you also get a glue-glue-glue vertex and even a 4-way glue-glue-glue-glue vertex, because you're taking the product of the F mu nu's, so you're going to get terms where this multiplies one of these, 3, and terms where this multiplies itself, 4. So the colour flow in QCD is considerably more complex than it was when the quarks are there. If you've got 3 gluons, this is your colourway interaction, and that's actually why gluon jets are fatter than quark jets are, because there's a whole lot more possibilities for gluon radiation than there are for the quark radiation. Okay, so that's the difference between QED and QCD, but for lots of the time we don't even really have to worry about it that much, because there are rules about what you do, right? You just have to add to your normal Feynman rules you would have used for QED some extra color factors. So something like this gluon splits to QQ bar, goes back to gluon, has a color factor called TR, which is just a half. Something like this with a gluon loop has a color factor CF. I have to say this, I'm sorry about the quality of this, because it looked hugely better on my machine. I'm not sure why it's come out so badly. But this is the color factor C sub F is 4/3. And finally, something new that doesn't even exist by analogy in QED, the gluon loop, which has a color factor of 3. Note, this is the biggest color factor we've got. The gluons interacting with gluons is a huge effect. Now, just to sort of finish on this theme that we can do these calculations, we understand what we're doing. The QED Compton scattering of photon on, could be an electron, could be a quark or whatever, out to photon again, has an analogy in QCD, photon in on quark, but it's gluon out and quark. And by analogy, it has the straightforward diagram and the cross diagrams. You can calculate this QCD Compton effect using the same Mandelstam invariants ST and U that you would use for the QED diagrams. The amplitudes for these two QED diagrams are given like this in terms of the spinors and the gamma matrices. Adding and squaring, taking care of your spins, you get this. So this is all just QED so far. To go to QCD, the e to the 4th that express just 2 electroweak vertices will be split into 1 electroweak vertex with the appropriate quark charge, not an electron charge, so that E sub I is just a 2/3 squared, something like that. And the other vertex is a purely QCD vertex with the strong coupling G. And we can rewrite that in terms of the fine structure constant and the strong coupling constant. Insert a colour loop of 4/3, and we get from here to here. So if you actually know how to do this easy one, it's not so difficult to also do the harder one in QCD. You just have to remember about the differing charges on the vertices and the colour factors, and you've got it. And you can do the boson-gluon fusion process that I've drawn here, where it's photon in, gluon, photon-gluon scattering to Q bar just as easily. Right? Those are the two processes that are used a lot when we're doing quark radiation. Now, before we get there, right, there's one more thing to think about. I told you that the fine structure constant is in fact not a constant. Possibly you knew that already, but what's it all about, right? When you're going, doing perturbative expansions beyond the leading order, so there's the tree order, you've got loop diagrams. And you suddenly start to find, when you do your calculations, that the calculations for the integrals around the loops are divergent, right? They're going to infinity. Unrestricted integration around the momentum of the loops, and you have to renormalize the theory, right? What to do renormalization? You make the constants of your theory, like the coupling, become dependent on the scale of the process. And if when you do this, it takes care of your infinities to all orders, you've won. That's a completely renormalizable theory. If you try and just fix it up and it only works to one order and you have to do more work at the next order, that's non-renormalizable and it's bad news. But in the case of the general fermion propagator, it means that we apply a correction term here which depends upon a concept of a sort of a bare charge, which we can never really know, right? And a high momentum cutoff. And in order to work with that, right, we write what is the fine structure constant as a function of the scale in terms of its bare value and its high momentum correction. Now, you don't want some unknown scale lambda in it, so what you do instead is you just define the coupling at one scale in terms of the coupling at a different scale. You write down how do things depend on scale if we know them at some low scale. And this is what it looks like for QED. And what it's telling us is that when we're going from, say, a low scale of around 1 GeV squared up to a high scale, say 100 or so, the coupling is actually increasing because of this negative term in the denominator. So the coupling that's 1 by 137 that we all know so well isn't actually true if you're working up at the scale of the mass of the Z boson, right? It's more like 1 by 125 than 1 by 137. It hasn't changed a lot, but it's changed a bit. Now, what of QCD? Well, the same diagrams exist in QCD, but whereas there the only thing we could do is add more loops, in QCD we can add a different type of loop. We can add this loop with the gluon loop in the middle of it that doesn't exist in QED. And what that does for us, it means that the equation that we get for the way that the coupling depends on scale now has a plus sign in the bottom, because this beta function here, right, it depends on 33 minus the number of flavors over 12 pi, right? And it's a positive number. Now, if it was just quark loops, we'd just have this bit, a 1 over 6 pi, and it would be negative. It's actually exactly the same as the 1 over 3 pi that happened there. The fact that one of them is 3 pi and the other is 6 pi is just a convention, right? It's not really any different physics in that. But the fact that, in fact, that's not the only term, there's also this term that turns it positive, that's a feature of QCD. And so what this is telling us is that instead of, as you go up in scale, the coupling becoming a little bit stronger, it's actually becoming not a little bit, but a lot weaker. So I've just put two plots there because this was the plot in 2009 of the strong coupling going down with scale, and I updated it in 2013 because you see at the end of the scale there, we've now extended it because measurements have been made at the Large Hadron Collider itself of the strong coupling. So we can see that things are behaving as we thought that they would. It's continuing to go down in exactly the same way. There's nothing new in the way that the coupling is behaving at high scale. And the value of this coupling at the mass of the Z is around about 0.1185 or so. But it's an extraordinary thing that we've got here. The new feature is that we have these extra loops, and that means that the coupling goes down, not up with scale, and that's what's giving us the asymptotic freedom. It will eventually, at some very high scale, be going to zero, or that's the way it looks. Whereas if you go to low energies, it's going up and up and up, and you'll have confinement. It's coupled so strongly that you can't get out. Okay, now, that's sort of some background. I just want to apply this now to the Parton model we had to show what happens when you get gluon radiation going on in your Parton model. So I had this simple picture of the vector boson hitting the quark. The way you can write that formally is that to calculate your F2 structure function, you do a convolution of the point-like cross-section here with the quark distribution, the probability that this quark had a certain subfraction y of the parton's momentum. Now in this case, because this is a point-like cross-section, we've got only delta functions, and the whole thing just collapses to the quark charge squared times the number density for the quark. We've essentially seen this before. I've just rewritten it in terms of a convolution. But now what happens if the quark that was coming out of the proton with subfractional momentum y, before it gets hit by the virtual photon, radiates a gluon and then lands up going in with a different momentum x. Right? Started with y, becomes x before it gets hit. What that means we have to do is add to this point-like term something to account for this. So we add to the point-like cross-section the cross-section for this sub-process, which is boson in, quark out, gluon out. That is actually, it's the very QCD Compton diagram that I showed a couple of pages ago, right? That's why that diagram is important. We know how to do it. So we're going to add this extra term to the point-like cross-section. Let's look at this again, this QCD Compton, and write it, try and write it very simply. We'll need a vertex factor for the boson QQ vertex. That'll just be given by the quark charge squared in terms of the usual fine structure constant. And then at this vertex, the GQQ vertex, alpha s. I could have said alpha and alpha s. We'll also need a propagator for the exchange. It's a quark that's being exchanged here. And the propagator for a massless quark that was supposed to be being emitted at this vertex is just 1 over its pt squared. It's acquired now a transverse momentum. Maybe I'll just comment on that for a minute. Although to make things clear, these Feynman diagrams had written the idea of a proton with a quark coming out and that's being hit and so on. Right? In reality, the approximation Feynman was really making was that this quark is collinear with the incoming proton. Right? However, if it's then going to do something like radiating a gluon, and it's this quark instead, this is no longer collinear. It's acquired some transverse momentum in the very act of radiation. And it's that transverse momentum, right, that we're using for the quark exchange propagator. Now, to make this calculation, we're going to have to integrate over possible values of pt, because we don't know what the unique value was. And the integral dpt squared over pt squared gives us a log term from the minimum to the maximum. Now, it's not difficult to calculate that the maximum PT this exchanged quark could ever have is the q squared of this incoming vector boson, right? It can't possibly have more than that, so q squared is the upper limit. The lower limit is not set actually by any physical lower limit, it's set by our ability to calculate. We here just put the lowest q squared at which we think we can get away with doing a perturbative calculation, right, called q0 squared. And what that means is that the value of alpha s at q0 squared should not be too small. It should still be such that we can make a perturbative calculation, right? Now, people have differed a lot as to how brave they are in how low they think you can go. And that's one of the issues. But we used to reckon at least 4 or 5 GeV squared was probably about as low as you could go. People have been braver and going lower in recent years, which contradicts part of what you said, that we're trying to keep above the mass of the proton squared. Okay, now, so the total cross-section depends upon these vertex charges, this integral over the propagator, and the final term, the splitting function. This is the probability that this splitting of a quark with momentum y into one with momentum x and a gluon with momentum y minus x, that splitting should happen at all, right? Now, if you want to see where the splitting function comes from exactly, you have to go and do that QCD Compton calculation I showed on a couple of pages ago, and you will find that this form of the function comes out of it. But just in the way, understanding it qualitatively, you can understand how this process contributes by just looking at the single diagram and then saying, and how probable is it that that split would have happened in the first place? Okay, so what we're doing now is we add this cross-section to the point-like cross-section. We know that this cross-section had also the quark charge squared in it, so we'll take that out, and we'll call this extra piece of the cross-section delta Q. And delta Q has in it the alpha s over 2 pi log q squared over q squared that we had here, and an integral. See if we, so where's my pointer? We've still got the dy over y qy integral, and then times the splitting factor that depends upon the difference between the fractional momentums y and x, right? So this is the extra piece that we're adding. And note, this is actually an extra piece of cross-section in addition to the point-like cross-section. But I've called it delta Q because when you look at the way that this gets into the formalism, right, this is our original point-like piece that gave us Q of x, and I'm calling this piece delta Q. In other words, I'm essentially taking what was a piece of cross-section and adding it into the Parton distribution function, adding it into the quark distribution function. I can illustrate what I mean again by drawing it, I think. That when we assume that this is happening, there's our proton and we're just taking one quark out of it. Then we say, no, on its way it's going to do this, it's going to radiate a gluon. Now what I'm doing when I add that into the quark distribution is I'm saying, actually I'll redefine what my proton was as containing whatever it originally had and this piece of radiation as well. So I'm now adding in an extra piece into my momentum distribution, and that extra piece has in it a logarithmic dependence on q squared. So we no longer have the Bjorken scaling that the q of x does not depend on the scale q squared. We have it modified a little bit by a log of q squared term. This is what QCD tells us. Now, we've therefore transferred this extra piece of cross-section into the Parton distribution function, and instead of writing q of x, we will now write q of x q squared to acknowledge the fact that it now does have a small logarithmic dependence on q squared. So Bjorken scaling is now violated exactly as predicted by QCD. Now, if I write this equation here as a differential equation for how fast do the Parton distributions depend on scale, I'll write it as dq by d log q squared, and it has alpha s over 2 pi, the integral over q and the splitting function. It looks like this. It tells us that quark distributions evolve with q squared in the log. So what we have now is we cannot predict the shapes of these distributions at the beginning, but once we know what they are at one scale, we can tell what they are at any higher scale because we know this evolution equation. QCD tells us that, right? It doesn't tell us the initial shape, but it tells us exactly what happens to it as you evolve up in scale. Now, I'm extending the formalism here because there's one more diagram that's important, right? Well, at leading order. At beyond leading order, there are loads more diagrams that are important, but let's stick to the simple stuff. It might not be that the quark we were going to strike radiated a gluon. It might be that what came out of the proton was actually a gluon in the first place, but it split to a Q-bar pair before it was struck. And we've got to account for this extra piece of the cross-section as well. And this is what's called the boson-gluon fusion diagram. I also indicated that a couple of slides ago. And by analogy with what I've done, as well as now having this piece, I will add to it a piece that depends upon the original gluon density at subfraction y and the probability that I get a split of the glue into QQ bar, which is this different splitting function. Right? So you've got the PQQ splitting function and the PQG splitting function. So the complete evolution equation looks like this, and they are called, sorry, that's the quark one, this is the gluon one. I'll come back to the gluon one. These two equations for how quarks evolve and gluons evolve are called the DGLAP equations. Right? This is sociologically interesting in the following sense, right? When I was brought up, these were actually called the Altarelli-Parisi equations, A and P, Altarelli and Parisi. And this was before the fall of the Eastern Bloc, right? And it wasn't until post-1989, 1991, and all the changes we've had in the world, that Western physicists appreciated that Dokshitzer, Gribov, and Lipatov had actually written down this kind of formalism quite a bit earlier, but, you know, Western physicists simply weren't reading it or noting it. After this enormous change in the world, it was recognized that this had in fact already been done, and these were relabeled the DGLAP equations. Which is a bit of a mouthful, really. But... Pardon?
Lipatov.
Oh, yes, sorry, yes, Lipatov. Okay, so we have the formalism for how quark distributions evolve. And hence, the F2 structure function should really be written in terms of quark and anti-quark distributions as x of q squared. And now here they are. This is against q squared, and it's split into different x bins. So if you are at a kind of medium x, x.14, x.18, x.2, actually it still does scale pretty well, right? That's why the original observation I showed you of the scaling, they were just lucky. They measured it at an x value where the scaling was pretty good. But as you get to higher momentum, right, more and more of the high momentum quarks are bleeding their momentum down by radiating, and hence the higher scale you go to, the more they've lost momentum. And that lost momentum here has gone to increase the ones that are at low x. There are becoming more and more of those. They're coming from here. And this is the way that, you know, the complete scaling violation plot looks. Now, I mentioned also that gluons will evolve, right? So for gluons, you've got two equations corresponding to gluon evolution. One is just looking at the quark radiation the other way around, looking at it from the point of view of the gluon, not the point of view of this quark. Right? and the other is the extra diagram glue, glue, glue. So here you get two contributions from quarks radiating into gluons with a PGQ splitting function, and from gluons radiating into gluons with the PGG splitting function. And that completes the fact that both quarks and gluons evolve. Now, this all looks great so far, and there's one tiny technical point about it, right? It all looks like these are small modifications to the quarks we already had. By, they're dependent on the log, they're multiplied by alpha s, right? So the change is as alpha s log q squared. But note, alpha s itself, as I said, 3 or 4 slides ago, it goes down with q squared. In fact, it's proportional to 1 over log q squared, right? So the quantity alpha s log q squared itself is not small, it's of order 1. Because alpha s is proportional to 1 over log q squared. So in fact, you can't get away with just considering one of these splittings. You've got to sum up all terms in alpha s log q squared to any power, because they're all the same size as each other. That formally is called summing the leading logs. And if I take this handy handbag diagram for what's happening, what it means is we can't consider just one split, we have to consider a whole ladder of splits, a ladder of gluon with gluon rungs, and sum that up. And when we look at that, right, you start out with a certain x, which is reasonably large, and with each piece of radiation you lose a bit, so it's ordered in x from the top to the bottom. It's also ordered in pt. You start out collinear, and with each radiation you gain a bit more pt. It's ordered in pt from the target to the probe. These are the dominant diagrams, and they're strongly ordered, right? Strongly ordered in pt squared. But they're not the only diagrams you might think of. They're simply the dominant ones in the kinematic regions that we had so far considered. Now, I just wanted to show you, I'm not going to go too far with sophistications in this, but at least one should have some appreciation for it. You can write the DGLEP equations as a coupled set of differential equations, and at leading order your splitting functions are here, right? That's Q splitting to Q with a gluon. This is looking at it from the gluon's point of view the other way around. And this is the glue splitting to Q bar, and this is the glue splitting to glue glue. That's at leading order. You might want to go beyond leading order, right? You might want to consider not just the QCD Compton and the boson-gluon fusion, but extra pieces of radiation at next to leading order and next to leading order. And what that will mean is that your original splitting functions will have extra terms depending on how many orders you're going to, right? So the bad news is it's more complicated, but the good news is it's all completely calculable, it's all known, and it's already been done for you by other people. At least it has to next to leading order. So you won't have to do it, you just have to use other people's results. It's been done, right? It has a few consequences. One is you can no longer really, if you're beyond leading order, just write the F2 down as a simple sum over weighted Q and Q bar. You actually have to take your Q and your Q bar and your glue and convolute them with functions allowing for these extra pieces of cross-section. Again, however, it's all done. We know what all these functions are, right, to do it at higher order. Another thing that happens is the longitudinal structure function that I told you was 0 isn't 0 anymore when you go beyond leading order. It has pieces contributing to it from the gluon and from the quarks. And when you think about it, it's kind of obvious that it wouldn't be 0, because the whole reason it was ever 0 was because we were scattering off spin-half quarks. But now we're admitting there's more than spin-half quarks in there. There are the gluons, they're spin-1 objects. And okay, maybe they split to QQ bar before you hit them, but you still notice that there was a spin-1 object in there. And that's why this is no longer a 0 quantity. But it's small, right? It depends leading alpha s. It's not leading order 1, it's leading order alpha s. So everything is still perturbatively calculable. Great. So now let's just, to get some feeling for this, let's look at how fast things evolve. Now, I've just been speaking about quarks, gluon to QQ bar splitting and so on, as if all quarks are the same. If you remember, we split the quark into thinking about the valence piece and the C piece. Now, the gluon only feeds, gluon splits to QQ bar flavor blind. So it doesn't feed into the valence quarks, it doesn't feed into the extra flavor, it only feeds into the flavorless overall QQ bar C. So when you evolve valence quarks, you don't have the gluon term. And what that means is, I'm drawing here a valence distribution. This is in the fractional momentum. The peak is at around about 0.2. Here is at q squared of 1 low scale, broadly what they look like. I'll show you how we find out what they look like tomorrow. But broadly they look like this, and as the scale goes higher, they bleed their momentum a bit down to lower fractional momentum, but not much, right? It's not a big deal. Now let's look at the total C, where x sigma is just a notation for adding up all the possible things that are in the C, all Q's, all Q bars. Let's take a case where you start at very low scale, q squared of 1, with a C that looks like this. This is not realistic. C's are piled up at low x. This is just a toy model to show you how it evolves. This is what the C is like, and there's no gluon. Now evolve it to q squared of 10, to q squared of 100. Pretty soon you start to lose this humpy shape because everything is bleeding down to lower momentum QQ bar, and you generate gluon out of it as well because the quarks and antiquarks are radiating gluons. So you start with no gluon and you pretty soon build some up, and you get rid of your original shape and just build up a low XC. Note the difference in scale here. By the time q squared is 100, the amount of gluon you've got is considerably outweighing other things. That's because of that Ca color factor equal to 3, which is larger than any other color factors. If instead I take a gluon with a rather silly shape like this and no C, and I evolve that, it takes almost no time before you lose the shape and evolve up the gluon, and it generates some QQ bar C. And by the time you've got to q squared of 100, you have these shapes. Look at the scale on that as well. Just see how fast it evolves. So appreciate actually that when you're going to high scale, frankly, valence quarks hardly matter at all anymore, right? It's all C and glue, and it's mostly all glue because it really just starts to dominate. So I think that's about it, and yeah, seems all right. 10 past 4, fine. Okay.